You know how we like connect ideas? Think about the classic example. Socrates is human. Humans are mortal. So you put that together, right? Socrates is mortal.
Right, simple logical step. Or connecting different facts to understand something bigger.
Yeah, like maybe thinking about Marie Curie. She studied physics, looked at matter, and matter's fundamental. So you kind of reason she helped us understand the universe. It's this basic step-by-step linking of facts we do all the time.
Exactly, taking premise A, premise B, and inferring C by finding that connection in the middle.
So here's where it gets interesting and maybe a bit surprising. With these super powerful AI systems, the large language models, we've been digging into some research for this deep dive, and it shows that despite all their power, they can actually struggle quite a bit with this seemingly simple step-by-step thinking.
The researchers call it two-hop reasoning, specifically.
Two-hop reasoning. Makes sense.
Yeah, it describes that structure perfectly. You need one hop, one step to get from your starting point, let's call it the source entity or SRC, to some intermediate thing, the bridge entity, BRG.
Okay.
And then a second hop from that bridge, the BRG, to where you want to end up, the end entity, END. The goal is to connect the SRC all the way to the ND through that middle piece.
Got it. John is the father of Paul. That's hop one, John to Paul. And Paul is the father of Ben, hop two. Paul to Ben. And you want the model to figure out the connection from John all the way to Ben.
John being the FRC, Paul the BRG, Ben the END. Simple enough, you'd think.
But the really surprising thing, the core finding in this research we looked at, is that these models can just fall apart on this task if there's irrelevant information thrown in.
Exactly. Just a few extra unrelated facts mixed in what the researchers call distractors can completely derail the model's reasoning.
Okay, wow. That feels counterintuitive for these powerful systems. So our mission today is really to unpack this. We want to understand why these big pre-trained models fail so badly, see how the researchers managed to fix it, and then, this is the really fascinating part, dive into the internal mechanics, like what's actually going on inside the model when it learns to do this properly.
Yeah, let's get into it. We've got the paper here, notes from the UC Berkeley team. It's pretty detailed stuff.
Okay, so first things first, what exactly are these distractors? You said irrelevant facts.
Good question. They aren't just random noise. In this research setup, distractors are other perfectly valid but irrelevant facts, or even complete reasoning chains that are put into the context right alongside the one chain the model should be following.
Ah, okay, so it's designed to test if the model can focus, filter out the junk.
Precisely. Can it find the signal in the noise? So back to the John Paul Ben example. The relevant facts are John is father of Paul, Paul is father of Den.
Right.
A distractor might be another set of facts, like Luke is father of Tom, Tom is father of Max, or maybe Sam is father of Joe, Joe is father of Mark. These are other valid chains, other potential grandfathers and grandchildren, but they have nothing to do with John.
Gotcha. So you feed the model all of that together, and this is where the surprise comes in. When they tested pre-trained models like Llama 2.7b.
Yeah, the base Llama 2.7b model, the results were, well, pretty stark. Looking at their table 1, if you give the model just the single correct chain, no distractors, it does great, near perfect.
Okay, as you hope.
But add just one distractor chain alongside the target one. The probability of the model picking the correct answer, Ben, in our example, just plummets. Add 5 distractors, it's barely doing better than if it just randomly picked one of the possible endpoint answers.
Whoa, okay, that's a huge drop. And it's not just getting it wrong randomly, is it? The researchers noted a specific kind of failure?
Yes, exactly. They described it as random guessing among all plausible conclusions.
Plausible conclusions. Meaning?
Meaning the model doesn't just guess any old token. It seems to look at all the potential end entities presented in the context, the right one, Ben, and the ones from the distractor chains, Max, Mark, and it basically assigns them all roughly equal probability.
So it can identify the type of answer it should be giving an end entity, a grandchild in this case, but it can't figure out which one is connected to the starting point, John.
Precisely. It sees Ben, Max, and Mark as equally likely answers connected somehow, even though only Ben is connected to John. Table 1 really shows this. The probability it puts on the correct answer is almost identical to the average probability it puts on the wrong end entities from the distractor chains.
That's fascinating. So this random guessing behavior, specifically when distractors are around, it really highlights a kind of brittleness in how these pre-trained models handle reasoning in context.
A surprising brittleness, yeah. You wouldn't necessarily expect it.
Definitely not. Okay, so that's the problem laid out. Big models struggle with simple reasoning plus noise. How did the researchers tackle fixing this?
Well, the fix turned out to be remarkably effective. Fine-tuning.
Just standard fine-tuning.
Targeted fine-tuning. They took the pre-trained model and continued training it, but specifically on a data set that included these two hop problems with distractors. Interestingly, most of their fine-tuning data only included contexts with the target chain and exactly one distractor chain.
Only one distractor in the training. Okay. And what was the result? Did it nudge the performance up a bit?
Nudge. No, it was like flipping a switch. They describe it as a sharp transition in performance from random guessing to near perfect accuracy.
Serious, yeah.
Look back at table 1 again. The rows for the fine-tuned model, the one trained on examples with one distractor, k equal 2, the probability on the correct end entity just jumps straight up to basically 1.00. Perfect accuracy.
Wow. Okay, that is a sharp transition. From totally confused to getting it perfectly right.
And here's what's really impressive. The generalization, remember, they mostly trained it on problems with just one distractor.
Right.
But when they tested that fine-tuned model on contexts with more distractors, 2, 3, up to 5 distractor chains, it still maintained that near-perfect accuracy.
No way. So it didn't just memorize how to handle one distractor. It actually learned a general strategy for ignoring them.
Seems like it. Table 1 shows that high accuracy holding steady even as you add more distractors. And this wasn't just a Llama 2 thing. They checked other models too, QN 2.5, Llama 3.1, OLMO, and found similar big jumps in performance after this kind of fine-tuning. The appendix tables show that pattern holds.
Okay, so fine-tuning on examples with distractors is the key to making the reasoning robust. That's the what. But the really deep question, and this feels like where the core academic innovation lies, is how does this work? What actually changes inside the model's network to make it go from random guessing to nailing the answer every time?
Right, and that's where they shifted gears into mechanistic interpretability, trying to reverse engineer the model's internal algorithm.
Looking into the hood.
Exactly. But doing that on a massive model like Llama 2 is incredibly hard. So they took a clever approach. They trained a much smaller, simpler transformer model completely from scratch, just 3 layers.
3 layers. That's tiny compared to the big guys.
Tiny. And they trained it on a symbolic version of the task. So instead of John is father of Paul, it might be like token A relates to token B relates to token C. Using single tokens for entities makes it way easier to track what's happening inside.
Okay, a controlled laboratory setting for AI reasoning.
Pretty much. And right away, this led to a really interesting, innovative finding about the necessary architecture. They discovered that this simple 3-layer transformer with just one attention head per layer was actually the minimal structure needed to reliably learn the task and show those distinct learning phases they saw before the slow random guessing bit, then the sharp jump to success.
So models with just 1 or 2 layers couldn't do it.
Apparently not consistently. They failed to learn the robust reasoning strategy.
That's significant. We've seen other work on simpler kinds of in-context learning, like just repeating patterns, where maybe 2 layers is enough. This suggests that even this basic 2-hop reasoning structure is inherently more complex computationally. It needs that extra layer of processing.
It really seems to, and to figure out how this minimal 3-layer model was doing it, they brought out the interpretability tools. Things like analyzing the attention logits, the raw scores the model calculates before deciding where to focus its attention.
Okay.
And also using something called the logit lens.
Logit lens, what's that?
It's a cool technique. Basically, it lets you take the model's internal state, its representation of information at any given layer, and project it directly onto the output vocabulary. It shows you which output tokens that internal state is kind of leaning towards or supporting at that point in the computation.
So it's like getting a snapshot of what the model is thinking about predicting mid-calculation.
Exactly. It gives you a window into the information flow.
Okay, great. So using these tools, let's break down that random guessing phase first. What did the attention patterns and the logit lens show before the model got good at the task, during that initial slow learning bit?
Right. So in that early phase, maybe up to around 800 training steps in their small model, the attention was, well, pretty unfocused. In the first layer, layer 1, they saw what they called a chessboard-like pattern. You can see it in their figure 2A.
Chessboard.
Yeah, basically parent tokens like SRCs and BRGs would attend pretty strongly to all the child tokens, BRGs and ENDs, from previous steps and vice versa. It was just gathering up all the connections it could find indiscriminately.
Like casting a wide net, grabbing everything.
Exactly, not selective at all. Then in layer 2, the attention patterns were also quite uniform, as shown in figure 2B. Still no real focus emerging.
Okay, still messy. What about layer 3, the final attention layer before the output?
So in layer 3, figure 2C shows the query token, that's the token triggering the model to give the answer, was attending to all the child tokens that came before it. That means it was looking at the correct bridge, BRGT, the distractor bridges, BRGNT, the correct end token, NDT, and the distractor end tokens, NDNT.
Okay, that makes sense why it would be confused then. If it's looking at everything equally, it can't pick the right one.
Right, but wait, remember we said it guesses randomly specifically among the end entities? Ben, Max, Mark in our example. Not the bridge entities like Paul, Tom, Joe.
Oh yeah, good point. How does that happen if layer 3 is looking at both bridge and end tokens?
But this is where the logit lens analysis was really crucial, a key innovative insight from the paper. Even though the layer 3 attention head was looking at both the BRG tokens and the END tokens, the logit lens showed how the rest of the machinery, the final processing layers leading to the output prediction, handled that information.
Okay.
It revealed that the value vectors associated with those attended tokens were combined in such a way that by the time you get to the final output logits, only the END tokens ended up having a significant positive influence. And crucially, all the END tokens, NDT and ENDNT, had roughly similar positive values.
Whoa, hang on. So the attention sees everything, but the downstream processing effectively filters out or cancels out the influence of the bridge tokens, leaving only the end tokens standing and all with similar importance.
That's exactly what their analysis suggests. The paper goes into the maths, but essentially the END tokens contribute positively to their own prediction, while the BRG tokens have contributions that tend to cancel out, leaving only the END tokens with similar positive scores in the final output calculation.
Okay, that's why it randomly guesses just among the end entities, because those are the only ones left with significant, roughly equal predictive signals at the very end. That's a much more specific mechanism than just it got confused.
Precisely. It's a very specific failure mode rooted in how the information flows and combines even after the final attention layer. Pinpointing this using the logit lens is a major contribution to understanding the failure.
Definitely. Okay, so that's the surprisingly detailed mechanism of failure. What about success? What happens inside the model after that sharp transition, when it starts getting everything right?
Now we get to the structured learning phase. After those initial 800 steps, the attention patterns completely change. They become incredibly precise and selective. The researchers describe it as the emergence of a sequential query mechanism.
Sequential query, like it learns to ask for the pieces of information it needs, one after the other, internally.
Exactly like that. It builds a step-by-step internal retrieval process. Let's look layer by layer again. In layer 1, that messy chessboard pattern disappears. Instead, you see a very clear token copying mechanism.
Token copy.
Yeah, each child token now attends almost exclusively to its direct parent within its own premise. So the target bridge token BRGT pays attention only to the target source token SRCT, and the target end token ENDT pays attention only to the target bridge token BRGT. Same for the distractor chains, but crucially, the chains are now kept separate.
So layer 1 becomes a filter. It learns to only pass information along the correct paths within each chain, effectively isolating the target chain from the distractors early on.
Exactly. It stops the information from mixing. Now, what about layer 2?
Layer 2, what does the query token do now?
In layer 2, figure 4b, the query token's attention dramatically shifts. It now focuses strongly, almost exclusively, on a target bridge token, BRGT. It ignores the distractor bridge tokens.
How does it suddenly know which bridge token is the right one?
Because layer 1 did its job. Layer 1 copied information from the target source SRCT to the target bridge BRGT. The query token also holds information related to the SRCT, since that's the start of the question. So now, the query and the target bridge token BRGT share a common signal originating from SRCT. That shared information allows layer 2 attention to lock onto the correct bridge.
Okay, that makes sense. Layer 1 sets it up. Layer 2 uses the query to retrieve the correct middle piece, the bridge. So layer 3 must find the final answer.
Precisely. In the structured phase, layer 3 attention, figure 4c, becomes laser focused. The query token now attends only to the target end token, NDT. It completely ignores the distractor end tokens.
And it can do that because, let me guess, because the query got the bridge information from layer 2, and the target end token got the bridge information from layer 1 copying.
You got it. The query token now effectively holds information about SRCT and BRGT. The target end token, ENDT, holds information about BRGT, thanks to layer 1. That shared BRGT information creates a strong link, allowing the query in layer 3 to selectively attend only to the correct final answer, ENDT.
Wow, so it really does learn this elegant step-by-step internal algorithm. Layer 1 isolates the right chain info. Layer 2 uses the query to find the bridge within that chain. Layer 3 uses the query now primed with bridge info to find the end entity linked to that bridge. That's the sequential query mechanism.
That's the core discovery of how the fine-tuned transformer solves this. It's not just pattern matching, it's executing a specific learned computational path through its layers, a genuine internal reasoning process.
And they didn't stop at just observing this, right? They built that simplified model.
Yes, the three-parameter analytical model, that was a clever move to test their causal claim.
Causal claims?
They hypothesized that the random guessing mechanism they saw in the untrained model actually caused that long, slow initial learning phase. And they hypothesized that the sequential query mechanism they saw emerge later caused the sharp, sudden jump to high performance.
Okay, so how did the simple model test this?
Their simplified mathematical model was built to only mimic the successful sequential query mechanism. It explicitly did not include the components that led to the random guessing behavior observed early on.
So it simulates only the good mechanism. And what happened when they ran that simulation?
The results shown in their figure 6 were really telling. This simplified model completely skipped the slow learning phase. It started learning effectively much faster.
Because the thing causing the slow phase, the random guessing mechanism, wasn't there.
Exactly. That strongly supports the idea that random guessing causes the slow learning. But crucially, the simplified model still showed that characteristic, abrupt, sharp phase transition to high performance right around the same point the full transformer did.
Okay, so removing the failure mode removed the slow start, but the success mode still produced the sharp jump.
Which provides really strong evidence that the sequential query mechanism is indeed the driver of that rapid improvement. It validates their explanations for both phases of learning.
That's really neat. Okay, let's just zoom out and recap this whole journey. It's quite a story.
It is.
We started with this pretty surprising fact. These huge, powerful, pre-trained LLMs can fail at simple two-step reasoning if you just add a bit of irrelevant noise, these distractors. They fall back into this weird state of randomly guessing, but only among the plausible end results.
Then we saw the fix. Fine-tuning. Just a bit of training on examples with distractors triggers this dramatic, sharp transition, making the model suddenly robust and able to generalize even to more distractors than it was trained on.
And then the really cool part, going inside the machine. Using smaller models, symbolic tasks, attention analysis, and that logit lens technique to figure out the mechanisms. We saw why the failure happens, that indiscriminate attention early on, combined with how the final layers process information, leading to equal scores only for the end entities.
And we saw the beautiful mechanism of success, the learn sequential query, how the model builds this internal step-by-step process across its layers, layer 1 filtering, layer 2 finding the bridge, layer 3 finding the end to execute the reasoning robustly.
Yeah, the level of detail in that mechanistic breakdown is really impressive. Plus, finding the minimal 3-layer architecture needed and then validating it all with that simplified model. It feels like a very thorough piece of work.
Absolutely. It stands out for connecting the macroscopic behavior, the learning curve, directly to the microscopic internal computations.
And this is cutting-edge research, right? From UC Berkeley, Tianyu, Hanlin, Ruiqi, Jiantao, Jiao, Song Mei, Michael Jordan, and Stuart Russell. You mentioned it's a preprint, still under review.
That's right. So it's fresh off the press, academically speaking, but it's already giving us these incredibly valuable insights into how these models actually work, or sometimes don't work internally.
And understanding this stuff, these mechanisms, it's not just, an academic exercise. It feels really crucial if we want to build AI systems we can actually trust, right? Systems that are reliable, robust, maybe even interpretable someday.
Couldn't agree more. If we want AI that can genuinely reason, especially in complex, noisy situations, we absolutely have to understand the steps they're taking or failing to take inside that black box.
Which kind of leaves us with a final thought for you, the listener, to chew on. Given how easily these powerful models were tripped up by simple distractors in basic two-hop reasoning before specific training, and given how intricate that learned sequential query mechanism had to be, even in a tiny 3-layer model, what does that tell us about the challenges ahead? What does it imply about achieving truly general, reliable, maybe multi-step reasoning in the massive, complex, often opaque LLMs we use every day? Something to think about.